a Zoom room for all of the students who are registered, so that
Welcome to ACE, your home for deep AI knowledge. Hi, everyone. I see some familiar names in the audience. Welcome back. And for those of you who have just joined an ACE session for the first time, feel free to say hi in the chat. But if you just want to sit back and learn, that's fine too. ACE hosts machine learning live stream sessions with researchers and experts in the field to help you stay up to date. We host multiple sessions each week, so if you'd like to be notified of when we have new videos and live sessions, feel free to subscribe. We have all the past talks archived on YouTube, but I definitely suggest also signing up as a member on our site, which is ai.science. That's really easy to remember. You can get notifications there, join social events, as well as get the materials on the talks, such as slides and the quick links to the papers themselves. Today, we have Matt Taylor and Leno de Silva joining us and speaking about their research, uncertainty-aware action advising for deep reinforcement learning agents. And to you who's watching, feel free to ask questions in the live chat and I will relay them to the speakers. And before we get started, I'll introduce the speakers, Matt and Leno, before passing it on to them. So today we have our reinforcement learning stream advisor, Matt Taylor, joining us. Matt is an associate professor at the University of Alberta and is a highly regarded and experienced researcher in the machine learning field. His focuses are in reinforcement learning and human-in-the-loop AI. We also have Leno, who is a postdoc machine learning researcher at the Advanced Institute for Artificial Intelligence, which is in Brazil, São Paulo. His research interests are in multi-agent reinforcement learning and transfer learning. So very happy to have both of you here. I'll pass the floor on to Leno.
Thanks, Susan, and thanks for the invitation. So we are going to present our work that was previously presented at the AAAI conference, one of the last conferences to be held in person. And this is a joint work done by me, Felipe Leno da Silva, that, as you might have noticed already, I usually go by Leno, Pablo Hernandez Leal, Bilal Cartal, and Matt Taylor. We have done this work while we were all working at Borealis AI, and right now I'm in Brazil, and Matt Taylor is working at the University of Alberta. So we are going to present by Matt introducing our motivation and some high-level ideas, and then I will be getting into some specifics of the method. So I will hand the presentation to Matt.
Awesome. Thanks, Leno. So as Leno said, I want to try to motivate some of this work by thinking about how do we get RL into the real world. So those of you who have heard me talk before, I am a huge fan of RL, but it's mostly in video games. And we need to get it out of video games and into the hands of people like you. So I actually recently gave a talk about how to identify good RL problems, how to de-risk them, and maybe how to tackle real-world problems. It's loosely based on someone else's paper. If you are interested in that, there's a bit.ly link for you. But what I'd like to focus on today is thinking about how and why we should cheat. So you might think that a reinforcement learning agent should go out into the world and just learn everything on its own and free from human bias. And that's a nice story. It can work. But a lot of cases, we want our agents to learn as fast as possible. So we want to think about how we could transfer information from another agent that's already there. Or maybe someone else, something else has already generated a bunch of data. We could use that to learn. Or we could think about explicitly asking someone else for help. Either another program, a human, another agent. Any of that is fair. So next slide, please. So a lot of my work has been motivated by this diagram in the upper right, where you can see a humanoid robot teaching a robot dog, or a person teaching a humanoid robot, or a robot dog teaching a human, thinking about how we can help an agent learn. And when we provide this extra information to the agent, we absolutely bias it. Now, this is a little contradictory because we really want to learn novel solutions. We want our RL agents to be able to outperform us and come up with things we wouldn't have thought of. But because humans have so much knowledge, it makes sense to me that we use that knowledge to help bias our agents, as long as those agents can eventually learn to outperform the humans and are not constrained by those biases. So you might argue that, well, Matt, you're just throwing extra short-term fixes at RL. Really, our reinforcement learning agents should be able to learn everything on their own. And maybe you should focus on just making better algorithms. But my stance is really, if we want to get RL into the real world, we want to give it every chance we can to make sure it succeeds. So next slide. So I wanted to briefly talk about off-policy learning, just as a way of trying to get this extra information into the hands of an agent. So for instance, you could have a data set. So you could have an agent that has performed some task, or a human, or another program. And if you are using RL to improve an existing solution, you probably do have that data. So instead of throwing your agent out into the world completely naive, you should probably use that data. Now, this is an area of current research, so trying to figure out how good does that data need to be, how much randomness does there need to be, how different can this policy be from how I want to act? Those are open questions. But right now, we do know that there are methods that can say, I am 95% certain that if I deploy my policy now, I will receive a reward of at least this. So what you could think of saying is, I've got a program that, I don't know, a program that's been trading stocks for me. And I am 95% sure I could take over with my RL agent now and get at least this reward. So you can have those kinds of guarantees. Next slide. And you can think about either trying to mimic the behavior of this existing system or outperforming it. So this is one way that you can use existing data, this off-policy. It's also called batch RL. It's a way of using existing data to help an agent learn faster. Next slide. But what we're going to be talking about today is something a little bit different, where we're thinking about there's another thing, there's another agent, there's another person, a program that could help us out, and we could ask for help. But it's a question of when and how we want to get this help. Next slide. One of the important things is that we're not just going to be thinking about subject matter experts. So there's been research where people were using humans to help robots learn. and they were focused on providing advice from roboticists. So if you have an expert, the method may be different than if you have just a person who is not optimal and maybe isn't really good at the task at all, but is still a lot better than random. So we're thinking about how we can use these people or other agents that are not optimal, not perfect, to get information out of them. Next slide. So we could think of, for instance, a person teleoperating a robot, providing a demonstration. This would be, for instance, watching someone trade stocks for you. You could have action advice. So you could say, hey, agent, what do you think I should do now? Should I go up? Should I go down? And that's actually what we're going to be focusing on today. But you could also think of things like feedback. So you can train a dog. You can also train a robot, good robot, bad robot. So if for instance, a agent is trying to fly a simulated helicopter, I have no idea how to fly a simulated helicopter, but I can tell the agent that was bad if it crashes. You could also think of preferences. So I could show you two agents and you could tell me which one is better. And over time, the agents could learn to perform the task that you want just based on this little bit of feedback. So I'm trying to emphasize there are many different ways that you can get advice into RL agents. This is just one of them. So next slide. We're thinking about how to get help. Who should initiate this? Well, one thing you could do is argue that, well, if you have a student and a teacher, the student is an RL agent and the teacher is some agent or programmer human that's experienced. So the teacher has more knowledge. The teacher should know kind of what's important. So one method is called importance advising, where, remember, in reinforcement learning, you have a Q value that basically tells you how good a state action pair is. So in this case, this I value is the difference between the teacher's estimate of the best action and the teacher's estimate of the worst action. So for instance, if you're in Pac-Man, if you're in the middle of a hallway and no ghost is near you, there's probably not a big difference in the different actions. However, if there's a ghost to your left and a power pill to your right, then which direction you choose is going to have a huge impact on whether you live or die. So that might be a good place for the teacher to provide proactive advice. So the teacher could jump in and give you this advice. You could also think of a correction method. So the student could ask, should I go left? And if the teacher thinks the student should go left, the teacher can say nothing. So to save some advice. Or you could think of predictive advising. If the teacher thinks the student should go left and the teacher thinks the student will go right, making the wrong decision, then the teacher could provide advice. So we're thinking about when is a good time to provide advice. Next slide. But you could also think, okay, so that's the perspective of the teacher, but what about the student? The student actually knows what's going on in its head, right? So the student should be able to figure out where it's uncertain. So for instance, we could look at the difference between the best action of the student and the worst action of the student. And if those are similar, then we could say, I don't really know what's going on. If my best and worst actions are too close together, I'm confused, and that's when I should ask for help. Or you could say, let's look at the states I've seen before. If I am in a new state that is not similar to anything I've seen before, that's a good time to ask for help. Or you could think of counts or pseudo counts. If I have not seen this state 3 times before, maybe that's a good time to ask for advice. Next slide. So you could really also think about a combination of both. You could have the student ask for help. You could have the teacher automatically provide help, and look at a balance of those. And people have done that. Next slide. But what I'm really interested in, and what we're going to be talking about today, is what if the help is not unlimited? So for instance, if you are interacting with a person, if you're bugging a person every time you want to ask for help, that better be a limited amount of times that you're going to bug them. Or you could think that there could be a cost. So if I'm asking someone to trade stocks for me, every time I ask them to should I do this or not, they're probably going to charge me for that. Next slide. So this talk, we're going to be considering a total budget. So the setting is the student can ask a teacher a certain number of times. So the student needs to figure out where to ask for help. And in Leno's paper, he was looking at where is the student uncertain. So he's going to tell us about how the student can estimate its uncertainty and then ask for help and show that actually does work. Next slide. The final thing I'll mention is where we're going in the future is thinking about what if there are multiple teachers. So what if you had teachers that had different specialties or different costs? How do you figure out who to ask? Another thing we're thinking about is what if there are multiple students? So if you're a coach and you're trying to coach a team of soccer players, you could tell player A to do something, but that means you are not telling player B. Or you could be a player on the field. You could either help player A or you could actually play the game. So this is where we're going, but now we're going to go back to the specific setting we're talking about today, where we have one agent, one student, one teacher, and the student is going to ask the teacher with at most some fixed number of times. So now I'll hand it back to Leno so that he can talk about the what we actually did in this paper.
Okay, Leno, could you unmute? Okay,
sorry.
awesome.
Thanks for the very good motivation, Matt. So now that we understand the background of the problem we were working towards solving here in the paper, we can have some high-level intuition of our method that was named requesting confidence moderated policy advice. So basically, we have one learning agent trying to solve a learning task. And before taking each action, so before taking any decision, the agent checks its uncertainty for the current state. If the uncertainty is too high, the agent will send a request for help to a teacher. So for example, here, Wally is asking, I don't know what to do with this box, so can you help me? And the teacher will provide some advice, for example, carry the box to the left. And Wally or the student will follow the advice, which we hope it will help the agent in the exploration. Right here in this work, we are assuming that this always happens. Every time the agent receives an advice, the agent will follow it. But you can also consider some settings in which the agent will reason over the advice, and sometimes it might not follow the advice. For example, if the agent thinks, okay, I received an advice, but I have a higher confidence than the agent who is providing the advice to me, so I don't follow it, or something like that. But in this paper, we will always assume that the agent will receive the advice and will follow it. So as you might have noticed, the key point in doing this is computing the agent uncertainty. So the agent has to be very competent on knowing when the agent knows what to do and when the agent doesn't know what to do. So before explaining exactly how we compute the agent uncertainty, there is a concept that I think it's very important for everyone to understand, which is the distinction between aleatoric uncertainty and epistemic uncertainty. So for understanding the difference, imagine that we are trying to model tossing a coin in heads or tails. So regardless of whether you have a perfect model of the task or not, there is some aleatoric uncertainty from the environment that tells you that 50% of the time you will have heads and 50% of the time you will have tails. It doesn't matter how much knowledge you have about the environment. This is the uncertainty you will have, which is inherent to the task. So this is what we call aleatoric uncertainty. But imagine you are trying to learn this model and you don't have this perfect information about it. So you have to do some trials and try to model what's going on. And let's say you have 2 heads and 1 tail. So you might build a model like the model one that is in the table. So you have, based on your observations, you will say that you have 2/3 of probability of having heads and 1/3 of probabilities of having tails. But since we have gathered a very reduced number of samples, we say that we have a high epistemic uncertainty in this model, which means that we have a high uncertainty on what's on the predictive capability of the model, which is not directly related to the uncertainty that comes from the task itself. And if we keep tossing this coin a lot of times, in the limit, you have zero epistemic uncertainty, in the sense that you have the perfect model because you have tried many times, and your model 2 in this case will have the same probabilities as the perfect model. But you still have the aleatoric uncertainty from the task, which is impossible to reduce. So relating this concept of epistemic uncertainty and aleatoric uncertainty to the advising, usually you have a situation in which if you have a high epistemic uncertainty, it means that the agent doesn't know exactly what you do because it has gathered very few samples of the tasks. So the agent needs advising when the epistemic uncertainty is high. When the epistemic uncertainty is low, it means that the agent has explored the task, or in special the state in which you are interested right now, a lot of times. So the agent has enough information about it and does not need advising anymore. The aleatoric uncertainty is from the task itself and does not change during training. So the thing the agent should know is how much of epistemic uncertainty the agent has, and try to use this for deciding when to ask for help or not. So we propose a way of estimating the epistemic uncertainty. This idea can be used both by deep reinforcement learning algorithms or regular reinforcement learning algorithms, where I give an example using a DQN-like network architecture. So if you're using, for example, DQN, you have the inputs from the state. We have some hidden layers for computing the values for each actions, and then the last layer will be a value for each action that corresponds to the Q value that you are trying to estimate, which basically is the quality of each action for this state. So if you are using this, you have an estimate for each of the actions, but you have no idea about how precise this estimate is. You just have the estimate and you have to decide using this. What we propose of doing is by having what we call, and some other papers also call it, as multiple heads in the network, which basically means that you have multiple predictions for the same Q value. So instead of having one value for each action that corresponds to a given state, you have multiple predictions for the same actions. So you have multiple heads for each of the actions. And you might wonder, why do we do this? So you have to think what happens during the agent training. The agent is starting by having a random neural network that will predict the Q value for each of the actions. And since all the predictions are random, even though you are trying to predict the same value, all the predictions will be very different one from another. And after the agent starts learning the task and is learning for a while, the predictions will be getting closer and closer because they're getting close to the real value. So you can use this as a kind of proxy of the agent uncertainty, because in the beginning, the variance between those values will be very high. And when the agent is getting closer to convergence, the variance will be reducing until it's very low. So we use this as a proxy of the uncertainty of the agent that we use in the advising framework for deciding when to ask for help or not. So you can see in the this in the first equation in the top left. We get the variance between all those predictions and normalize it by the number of actions, basically. You might think in other ways of extracting the uncertainty from those predictions, but we do this in this paper. And it's pretty simple to just recover one single prediction of the Q value for deriving the policy, for example. And how to do this is shown in the equation that is below. That basically you take the average of all the Q value predictions you have for any specific action. And for doing this, we need this parameter that we call as H, that is the number of heads, or basically the number of different predictions that we have for a single action. And before actually testing on the final environments, we have analyzed a little bit what happens with our uncertainty during the learning process to see if it's really a good idea of using this in the advice framework. And you can see the result here. So basically, depending on how many heads you use, it's smoother or not so smooth. But the basic trend is that in the beginning of the training, the uncertainty will be very high, and after the agent is gathering more and more knowledge, the trend of the uncertainty is to reduce. It's not perfect depending on the parameter you use, but since we are using this for advising and it doesn't need to be completely perfect all the time, so it seems to be a very good method of estimating the agent uncertainty. And then we proceed to the experimental evaluation in actual environments.
So, Leno, there are some questions here, if you don't mind answering them a little bit.
Sure, no problem.
The first question is, how would you say if this is similar to curriculum learning, or is it not similar at all?
So curriculum learning, basically, you have a lot of small tasks that you solve, and then you reuse the knowledge for solving a new task, for example. It's related in the sense that you are trying to use the knowledge from one source to another, but the practical way how the advising and the curriculum learning works are not very related, because curriculum learning is more related to how to use the knowledge from one task in another, related but different. And advising is more related to how to reuse knowledge from another agent into a different agent. So it's like related concepts, but the practical way of how to implement those ideas are kind of very different.
And if I could interject there, we recently put out a survey on curriculum learning for reinforcement learning. If you're interested, you can find that on arXiv. But I wanted to point out that this type of training could potentially be used for curriculum learning. So for instance, if you had multiple advisors, in some cases, it may make sense to not ask the best advisor. You may want to ask the advisor who is just a little bit better than you. So that way you could build an implicit curriculum out of advisors. So you start listening to the worst one, and then you listen to better and better and better people over time. And you can actually learn faster that way than if you just listen to the best person. So it's kind of a cool counterintuitive fact, except when you think about scaffolding in school. So you don't start trying to learn calculus, you start learning the simplest stuff first. So anyway, that's I thought the questioner might find that interesting. That is not what we're doing here, because we assume we only have one single trained teacher.
Gotcha. Yeah, that's a very, very good answer. Hopefully that was helpful. One other question is for the previous slide with the graph. So they're asking, what are the spikes in the graph when in the purple line, the h equals 2? What are those spikes?
Since we are using only 2 heads in this example, there is a lot of variance coming from the training process itself, because we have only 2 predictions for getting this value. So the prediction in this case, it's not as good as if, for example, you use 100 heads. And that's why you have the spikes, because it's not very precise. But I think for the reason why we are using this uncertainty for defining when you are asking for advice or not, it doesn't matter that it's not, that the prediction of the uncertainty is not perfect, because if you ask for advice in a time that you don't really need it, you waste a communication, but nothing terrible will happen. You're gonna continue learning in the same way. So hopefully you don't spend a lot of communication asking a lot of times when you don't need. But if you do it sometimes, and in average you are asking in the right timing, that's already perfect for the use of the advising framework. If you need a very precise quantification of the uncertainty for some reason, this might not be the best method for doing this, or you have to set a very high number of heads so you have a more precise estimation.
Gotcha. Thank you. I think that's all the questions for now.
Okay, great. So after we have validated that, at least at principle, it seems to be a good idea to follow this estimation of the uncertainty for asking for advice, we evaluate our method in 2 different domains, in 2 different levels of complexity. The first one is a pretty simple grid world environment where the agent is trying to reach Canada. And for the teacher, we use an optimal demonstrator, which is an agent that knows the perfect policy for solving this task. And in the other environment, which is way more complex than the grid world, it's the Pong Atari game, which basically we are trying to train one agent receiving advice from another trained agent that doesn't have the optimal policy. So we get one agent trained in the task for some episodes until the agent learns a competent policy, but this policy is far from the optimal policy for this game. So we are receiving advice from a competent agent, but it's not a oracle agent. So the answers will not be perfect every time. And for comparing if our method is useful or not, we compare it against not using advice at all. So basically only using the base reinforcement learning algorithm. We compare it against giving advice in random timings. So just before the agent takes every step, the agent has a probability of asking for help, completely disregarding its knowledge or any kind of heuristics for when to ask for help. And we also compared the importance advising that was introduced during Matt's talk, which is kind of like the state of the art of advising algorithms, which is a very good heuristic for defining when to ask for help. Basically, the difference between the best action and the worst action in the point of view of the agent. So before I explain the results, let's understand what's going on. So basically in the top graph, you see the sum of received rewards in the y-axis and the number of training episodes in the x-axis, which means basically that we are observing the performance of the agent over time. So In the top graph, as higher the value, as better. And in the bottom graph, we are seeing the what we call as budget, or the number of times the agent used an advice. So in the bottom graph, you are seeing the number of the advice that was given to the agent over time. So in this one, as lower the value, as better. And if we compare the results that all the methods have achieved, one nice thing to notice at first is that basically all the advising methods, even the random one, achieved a better performance than not using advice at all. So the first finding of the experiment is that it's a very good idea of like having an expert agent providing some guidance to the learning agent. And our method have outperformed not giving advice, and also giving advice at random timings, but it had the same performance as the importance advising that was the state of the art before. Maybe because the environment was too simple and didn't have a lot of possibilities of improvement, but it doesn't mean that it's not a good idea of using our method, because we can see in the bottom graph that our method has a better use of advice. So basically, if you remember the equation that was explained by Matt, the agent will compare the best and the worst action for that particular state, and will give advice if the difference is too high. It means that every time the agent is going to that same state, the teacher will be providing advice and providing advice and providing advice. So you use a lot of communication and a lot of advice, regardless of whether if the agent has already learned or not. And in the case of our method, after the agent figures out that the uncertainty is low for that particular state, the agent stops asking for help. So as you can see in the bottom graph, we can achieve the same performance as importance advising while you're using much less of advice, which is a very positive result.
A quick question here is the importance advising well, I guess I wouldn't say subset, but rather like, is RCMP like an improvement or optimization of importance advising in general?
I would say that RCMP follows the same high-level idea that you need a heuristic for defining when to ask for help and why you don't need help. But it's not. It doesn't follow exactly the same specific idea or the same equation. It's a different way of computing the uncertainty. And importance advising is one heuristic, and RCMP it's another heuristic, basically.
Gotcha. Thanks.
So now we are going to see the results for the Pong environment, which is more complex than the Gridworld. And the graphs have the same semantics. So the top graph should be as high, the value should be as high as possible, and the bottom graph should be as low as possible. And as you can see here, again, we have the situation where all the advising methods outperform not giving advice at all. And in this case, we have a better performance using RCMP than using importance advising in this more complex environment. And we also visualize the same result in terms of use of communication. So it's very good that we can observe in our method that after the agent figures out that it doesn't need advice anymore, it stops asking. And in the case of importance advising, the agent will ask forever until all the budget is used. So as a summary of our experiments in this paper, our method have performed better than the baselines across domains with different complexity levels. In this case, the Pong game and a Gridworld domain. And receiving advice was advantage, both when we are using optimal or non-optimal demonstrators. And RCMP is an effective and flexible way of estimating the epistemic uncertainty, at least for the purpose of receiving advice. And as a more, let's say, high-level conclusion, what we show in this paper and in some other related papers that we have been working on these ideas over the years is that additional help is necessary for scaling up reinforcement learning. As Matt has said, giving some bias to the agent, it's very good when you can afford it, and when you don't restrict the agent in learning the best policy. And action advising is a promising way of doing this. And we have shown that we can bias the agent exploration in a positive way in this paper. And which is what is very nice with this idea of action advising is that it's applicable in many scenarios. So you can have human teachers providing some advice. You can leverage legacy systems if you have a system that works for a given task but has nothing to do with artificial intelligence at all. You still can leverage this legacy system for providing advice to your learning agent. And you can also do the same idea that we have explored here in multi-agent learning, having agents that are learning together, advising other agents in the system so that the system as a whole learn faster. So I have to thank you for the invitation, and I will take more questions if the audience has some more.
Awesome, thanks. Okay, one question is, in the opening, Matt emphasized the industrial applications as part of the motivation of this work. And what are the implications for this work that could potentially be applied to industrial applications?
Yeah, so I tried to say we need to get RL out of video games and into the real world, and then Leno presented our results in video games. So way to go, Matt. No, but I think so. This last slide in particular, I think, is relevant. So if you have a legacy system, then you could use it to bootstrap your RL agent. So for instance, if you are controlling a plant and you've got some carefully hand-tuned way of responding to different changes, then your RL system could query that legacy program. And hopefully that would be relatively easy to do, but still provide a very significant speed up in your learning. Because one of the biggest challenges to RL is that very poor initial performance and the cost of exploring. So if you have, so for instance, if you have a self-driving car that's learning, and the car is really interested in what happens when you crash into a tree, it doesn't matter how interesting that is, there should be someone stopping the car from doing that. So for instance, the difference between going straight and turning left into the tree has a very different Q values. So that might be a time where the teacher steps in and forces the system to learn to do the correct thing and try to avoid those bad situations. So that's a very extreme example, but my hope is that this kind of additional help will allow us to get RL agents into the world without having that poor performance and without causing disastrous exploration. Hopefully that answered the question.
Yeah, I hope that's, I think that's helpful really to, well, Amir asked that as well. So I'm sure that'll be good. Actually, on the topic of exploration, another question is, so the student, right, it'll see unfamiliar or uncertain situations, and it has stored like historical states, so it knows that, you know, some of these are unfamiliar. So when it's doing more exploration, right, did you notice that it's likely to be asking the teacher more? And I know you mentioned there's like a total budget, where they can't be asking every step, right? But is it at the beginning, when there's still quite a lot of budget? Is it when they explore that they ask more questions of the teacher, or is it it doesn't have to be when they're exploring, just some other situation?
So I think in the beginning of training, it's the time where the agent asks more frequently because the uncertainty is very high in most of the states. But after the agent has been exploring for a while, what will happen, and what is very interesting for us, is that the agent will not ask anymore for some states that it has seen before, but you start asking for unfamiliar states. So let's say the agent applies some exploratory random action and then just show up in a state that it has never seen before. And in this case, the agent will ask for help, even though it has been learning for a while and is not asking for help anymore every time as it was in the past. So I think this distinction of the agent being able to figure out when it knows what to do, when it doesn't know what to do, without only using hard-coded number of steps, it's a very positive thing for the learning process of the agent.
Okay, one more question is, could this be a type of introducing active learning into reinforcement learning?
Yeah, I would say that this is kind of the same high-level idea of active learning, but implemented in a reinforcement learning way, let's say. Basically, the agent is trying to figure out when the samples are more useful and asking for them to the teacher in those situations. So it's the same high-level idea. You could even say that it's active learning, reinforcement learning.
Well, and in this case, it was in this state, should I ask for help or not? You could also think of an agent planning ahead and being like, I don't know what happens if I'm in Calgary. Let me go to Calgary and ask the teacher about it. Or you might think, in some cases, if you have a simulator, you might be able to teleport. So you could say, oh, I don't know anything about this part of the state space. Let me teleport over there and ask the teacher. And that feels a little more like active learning, because then the agent is less constrained and has more power to query the oracle. But it's very much an active area of research, and there's plenty of places where you cannot teleport. So where the community is still figuring out exactly how to leverage existing ideas in active learning in an RL setting.
Gotcha. That's really exciting. On that note, there is a follow-up question. So active learning might have an issue that students can be distracted, and could that be an issue here in the, I guess, frameworks that you've presented?
I think distracted in this specific reinforcement learning setting will basically mean that the agent will be asking for help a lot of time, and this will make the agent waste a lot of communication. This wouldn't be a very big problem because the agent is constrained in the number of advice that it can ask. And hopefully, in the worst case, you just like finish the episode because the agent has received some advice to go to the goal and has finished the episode, and then the agent will start over in the beginning of the task, and this hopefully won't happen again. I think in practice, I have not seen a huge problem in this regard. It could possibly become a problem depending on the task, but some things that we do, for example, restricting the number of advice that the agent can receive, kind of tend to avoid this problem, or at least.
Yeah, it does sound that that constraint solves quite a lot of concerns or questions that people have thought about. So that's pretty great. One more question is, so where does this fit in exactly the feedback loop in the RL environment? So, like the interactions between the teacher and the student happen before they pick an action, and then let's say they get the reward, they calculate the Q values and stuff. Like it happens all before that, and everything else kind of proceeds as normal, right?
Yes, so basically the agent, before choosing the action, might ask for help. And in case it asks for help, everything else in the environment will just behave as if the agent has chosen the same action in the first place. So nothing changes in terms of the agent interaction with the environment. And what changes is just like the reasoning process of the agent, that instead of picking the action that would pick in the first place, it receives some external help on choosing the action.
Gotcha.
And you can really, like Leno said, it's really just changing the action selection mechanism. You could also think of treating this teacher advice as a different kind of knowledge. So you get data by interacting with the environment, and you get data from the teacher. Right now, we just take that data from the teacher, change what action we're executing, and throw it out. There should be ways of using that very high value information more. We should be able to leverage it to save it somehow. And that's really exciting for future work. But one of the things I like about this method that Leno presented is it's relatively simple and it works so well. So that's kind of cool. So this is always a risk when you're publishing, right? If you're publishing something, you better make it look complicated. So we were lucky that we got some reviewers that were like, actually, it doesn't need to be super complicated. It works. This is cool. So in that respect, I'm very thankful we got the reviewers we did.
Awesome. Yeah, that's really cool. Okay, I think there's one more question. So you mentioned, I think this is more regarding the importance advising, actually. It's, like there's some sort of spread of the rewards of the action, and, this is something the student doesn't know. And what is the main reasoning behind decoupling this from what the student knows, right? Like, could they not build it into the student, if that makes sense?
Not sure. So there you can think about the teacher knows, let's say the teacher is perfect. The teacher knows the actual Q values, so knows exactly how important an action is. The student is learning, but the student actually has a better idea of what's going on in its brain. So you could argue why one of these is better than the other, and you could also combine them by having the student ask questions and have the teacher provide advice. If you had the ability to do transfer learning, then you could just take those Q values out of the teacher and stick them into the student. And that would be the easiest way to do it. In this work, we're assuming you can't do that. So for instance, you have two robots that can only communicate actions. They can't swap out brains. Or the teacher is a human and does not have Q values to give you. But if you could actually access the teacher's Q values, then you should just copy them over to the student.
Gotcha. Yeah, that makes sense. Those are different approaches, and it makes sense that what the question was. There could be other approaches that do that. It's not saying that you can't do that. It's just not this approach in particular. Okay, one other question. There's quite a lot of questions here. Everyone's very curious about this work. How is the uncertainty threshold decided given the budget?
Okay, that's I think this is one of the hardest things to define in this approach. And basically what we do is that you can observe how the uncertainty of the agent is progressing over time. So you can have an idea of the kind of, let's say, the size of the variance that the agent usually have when it's uncertain and when it's certain. I think one very important very important future work would be thinking on adaptive methods that could figure out the threshold itself. We don't have this yet. So what we basically do is we try to, let's say, guess what would be a good threshold by observing how the reward function works in the environment and trying to guess what would be a good threshold. But there is not a very good answer for that right now. This is one aspect of the work that would be very interesting to explore in further work.
Awesome, thanks. I think that's all the questions for now. There was quite a few for sure, and thanks for answering them. I think that really helped both the audience as well as myself. So yeah, any kind of final comments or conclusions to wrap up?
Do you want to start, Matt?
Sure. I would just reiterate that reinforcement learning is awesome, but when you're bringing it into the real world, you're gonna want to find all the tricks you can. So this is one way of providing bias to the agent. There's many ways to inject human knowledge into agents and figuring out the trade-offs between helping the agent learn, but also worrying about limiting what it can achieve. Because if you impose too many constraints, the agent will be unable to find solutions that you did not already think of. So it's to me, it's a very exciting area of open work. And hopefully, as we get more deployed reinforcement learning agents in the real world, we will start to better understand best practices for the amount of bias you should have when you are when you are deploying your agent.
Yeah, I think those kind of approaches where different agents can communicate itself and share knowledge and stuff like that, especially without having to communicate very low-level information like gradients and Q values, will be very important when we start having reinforcement learning devices in our home or in our work environment, etc. Because those agents might have different manufacturers, and you might not have a lot of information about the low-level implementation of each of those devices. But it doesn't mean that you cannot reuse a lot of the knowledge that those agents are gathering by exploring the environment and use it to have all your artificial intelligence environment of devices learn faster. Because they can be all be communicating with itself and changing some experiences and exchanging suggestions. And I think this is a approach that is very promising for this specific area of how to reuse knowledge from devices that you don't have a lot of information about its low-level implementation.
Gotcha. Thanks so much. Really exciting stuff. Really good points. So yeah, once again, thank you both Matt and Leno for being with us here and speaking, and as well as the audience for tuning in today. I'm sure you learned a lot. I'm hoping you did. And thanks so much. Take care now.
Thank you. Bye-bye.